Hello and Assalamu alaikum. My name is Pakisha, and in this video, we will be discussing adders, different types of adder in quarters. In previous video, we have discussed adders, half adder and full adder in Proteus, and similar, and have seen their outputs, how they work by simulating them. So in this video, we will be making adders, different types of adder and subtractor in quarter software by using Verilog HDL coding. So the first type of we are using, so there we have a half adder and we have full adder. So the half adder has uh, two inputs and they add together, and the most significant digit is after them is C, and the other is the sum. So but in full adder we have carry in and carry out, uh, and also we have the sum of um, the two inputs, and when multiple adders are combined together, they become a ripple carry adder. So first Verilog code we have over here is of Verilog code for unsigned 8-bit adder. So here we have started the code with module, and we have given this name the code B, and this A B. So A and B are two 8 bits input, and C in is also an input. We carry in. So and this is sum, and sum is 8 bit output, and there is also a carry out. So we have assigned the var over here, and we have also assigned this temp, and this is the adding process over here, a plus b plus carry in. So our output is 8-bit, as it contains the carry out. Sum is 8-bit, and this is 9-bit. The ninth bit is the carry out, whereas the sum we got is the 8-bit number. So I will start the simulation. So here our code has compiled. So this is our RTL view. You can see over here. This is a circuit diagram for our code, and I will show you now the waveform. So here I have given the input, that is 00110010, that is 50. It's a 8-bit number, so I can give a larger value. And in the B I have given this 1010010, this is 162, and carry in is 1. So after compiling the code, I get this. Yes, 50 and 162, and this is carry in 1, so the output is 213. So it's doing addition. So now we'll move on to our next code. So here we have the second case in which we are using carry in input. So in the previous case we have also used the carry out with the carry in, but in this case we are only using a carry in input. So you can see our carry input is the 1-bit number, and A and B are the 8 bits inputs, and output is a 8-bit sum. So we are using this sum of a plus b plus c input, that is carry input, and this sum is, that is output is 8-bit number. So in RDL view we can see that this is the circuit diagram that the circuit has given to us, cortex given to us. This is the carry in. You can see where this is the carry input, this is A and this is B, and we have the output over here this side. This is the output, and these are the 8-bit inputs. So after that we have this waveform. I have given inputs that is 4 and 1, and a carry input is 1. So the output we get is 6, that is 4 plus 1 is 5, 5 plus 1, it gives us 6. So this was our second case. So in the third case, we have simple addition without using um, carry in or carry out. So A and B are 8 bits input and sum is a 8-bit output. So circuit diagram of this is simple uh, adding case. So this is A and B are the inputs and sum is the output. Whereas in uh, waveform visualization, we can see that I have given 6 and 2. The sum is 8, that is 0 0 0 0 1 0 0 0. In 8 bits it is 8. um, in binary it is this, and in decimal it's 8 number output. So this is our fourth case according to the steps we are using, according to the pattern we are moving on. So in this case, we are only have carry out without the carry in input. So this is the carry out 1-bit carry out output, and this is sum output, that is 8-bit, and A and B are two inputs of 8-bit inputs. So these are, sum is also a 8-bit output, and the ninth bit is carry out. So in this case, we have this A in circuit diagram. We have A and B two inputs, and this a ninth bit is a carry out, and this 8 bit is a sum. So output. So when we move to on towards the waveform, I have given this 6 and 10. So the carry out is 0 because it was 8-bit number, and the ninth bit would be the carry out, whereas the input is small, and it's fulfilling in the 8 bits of the sum. So the carry out, which is the ninth bit, is 0. So this is the output in the decimals. If I change it to binary, uh, it looks like this. So now we'll move on to our next Verilog HDL code. So in this fifth case, we are designing a Verilog HDL circuit that is unsigned subtractor. So in this unsigned subtractor, we are using borrow, and this is subtract is the output, 8-bit output, and two inputs, that is the same like in previous ones, that are A and B are two 8-bit inputs, and we are using this borrow, a single bit borrow. So this borrow is the ninth bit, and the 8-bit, the first 8 bits are the output value, the subtracted value of A and B. So this is our circuit diagram of the subtractor case. A and B are two 8-bits inputs, and the ninth bit is the borrow, and the first 8 bits are our subtracted output. So we move on to the waveform. So I have given 10 to the first input and 4 to the second input, and the borrow is 0 because these are 8 bits inputs, and 10 and 4 come in the first 3 inputs. So it becomes 9 bits is 0. So the subtracted output is 6 in the unsigned decimal. If you convert the binary, you can see that this is our input. So now we'll move on to the ALU that we have designed. Okay, so the sixth question we have over here is construct and implement the logic of a 4-bit arithmetic and logic unit ALU. So the ALU is mathematical logic unit, which is simply known as a calculator or any system that can perform multiple operations. So in this ALU, we have to perform 10 functions. Um, so I have used over here with two inputs of 4 bits each input. So A is a 4-bit number and B is a 4-bit input. And this is the operator, uh, or you can say a selector case for the 10 cases. So which we will perform individually in waveform. So here we have the output is a 4-bit output, and here we are using case statement, and in this case statement we have these 10 cases um, of the functions we have to perform. So when we will give to the operator 0 0 0 0 4-bit input, we will be performing additional case a plus b. Similarly, for we will be giving 0 0 0 1, we will be performing subtraction case, and these are the 10 cases I have selected. So this is a multiplication case, and this is a similar cases. So if you see the circuit diagram, so this is a huge circuit because of multiple operations that are being performed over here. You can see these are different gates used over here, and mux are being used, latches are being used for storing the data. This is a and B or two inputs, and this is the operator case, and this is the output is 4-bit output. So this is the addition, multiplication, and the subtraction case over here, and the OR gates, NOR gates, and gates are being used. So if we go or move on to the waveform, so here to the operator, if I give the first statement, that is 0 case, and to this I give 0 0 1 0 and 1. So here we can see when I have given the input 3, 2 and a 1, so our output is 3, and because we are using the addition case, this was our operator selection we have done, and the A plus B is given to us, that is 3. So these are very many cases, so it would take a lot of time. So a similar way they are being performed. If I show you how we can use a subtraction case, only in this operator case we have to select it one, sorry, one, and we have to run this simulation, and it will do like that, perform the next function and the next function and the next function by just changing these operators. And if we want to change the inputs, we will change A and B. So that was it from this video. Thank you very much.